In this tutorial, I will share the essential formulas and conversions needed for the CWI exam. We'll also solve sample problems together. Let's get to it. For the area of the circle, it is given by pi times radius squared or pi times diameter squared over 4. The shortcut for that one, for pi over 4, is 0.7854 times diameter squared, which is given here. So pi is equivalent to 3.1416. So that is the numerical equivalent of pi. So to discuss some terms here. So we have a circle. This is the center of the circle. Then the diameter of the circle is, you have 2 points. You draw a line passing through the center of the circle through the 2 points on the opposite ends. That is called the diameter. For the radius, you have a circle again. Then you have a center of the circle here. Then it is just 1/2 of the diameter, which is like this one. It is a line drawn from the center of the circle to another point inside the circle, or throughout the circumference of the circle. That is the radius. The area of the square or the rectangle. So this is just the area is equal to length times the width of the cross section, or can be width times the thickness. So for example, you have a rectangle. You have the length and the width here. So you just multiply them. Percent elongation is defined as the measure of the difference between the final gauge length and the original gauge length divided by the original length of the specimen. This is a measure of strain and can determine if the body is ductile or brittle. Meaning to say, if you have a percent elongation greater or has a large number of percent elongation, meaning to say the body is more ductile, meaning it can stretch more before it will break. But if you have a small percentage elongation, meaning the gauge length or the specimen broke at a smaller length, meaning that specimen is brittle. So it determines the ductility of the specimen. So to illustrate that, this is the original gauge length, L sub O for example. Then this may be the change in length. Call that as delta L. Then this entire length you see here is the final gauge length, or L sub F or LF. So that's how these percent elongation looks like when you test the specimen. So how about the percent reduction of area? So the reduction area happens during the elongation of a body wherein the cross-section of the specimen gradually becomes smaller. The percentage reduction in area measures that. So in mathematical terms, it is the original area minus the final area over the original area. So what happens when you pull a specimen out? It gradually decreases in area. So that's what happens. So this is an exaggerated figure. So at this point, there's a reduction in area happening. So maybe this is the original area, A sub O, and then this is the final area, A sub F. So you measure the difference between the two. The tensile strength measures the load it takes to break the specimen. It is a simple measure of force over area. So if you're familiar with pressure, it is synonymous to pressure. So this UTS is the ultimate tensile strength. So this ultimate tensile strength measures the strength of the material at its breaking point. That's why the Pmax here is the load to break the specimen, and the area is the specimen's original cross-sectional area. So to illustrate that, the cross-sectional area is the cross-section normal or perpendicular to the force. For example here, if you have a specimen, a pipe, then you pull that pipe in this direction. This is the normal force or perpendicular force to the area of the pipe. So that's how you measure the cross-section of the specimen. So it should be perpendicular to the cross-section. The force should be perpendicular to the cross-section. So for example, you have a force here of 10,000 pounds. You just divide it by the area here. So if you have an area of a circle here, you just utilize the formula earlier, pi times r squared, or pi over 4 times d squared, where r is the radius and d is the diameter. Then you divide those two, the result of those two. So this formula applies the UTS formula for a full section of a pipe. So the formula you see here is the Pmax is just the load in pounds or in Newton for SI unit. The 0.7854 you see here is the one that I mentioned earlier, which is pi divided by 4. The OD is the outside diameter of the pipe. Then the ID is the inside diameter. You can write that formula as well as UTS is equal to Pmax over pi over 4 times OD squared minus ID squared. Later, I have an example showing this formula and how to use them. Next is the yield strength. Yield strength is measured by the load applied at the offset divided by this original area. The offset is the arbitrary point of the material's elastic limit, and when exceeded, the material will no longer return to its original condition. So the yield strength of a material is defined as the offset, load at the offset, meaning the force at the offset here, say for example, this is the offset, this is the yield point, this is the proportional limit, and this is the elastic limit. This is the stress and strain curve, if you're familiar with that. So after reaching this yield point, the material will no longer return to its original position. So for example, you pull a force here, then it reaches beyond the yield point, it will no longer revert back to its original position. For example, this is the point of the original position of the bar or the specimen. So if you exceed the yield point, it will no longer return to this original position, meaning this is the deformation. So the cross-sectional area you will use there will depend upon the specimen. So if, for example, that is a rectangle, you will use the width times the thickness. So if it is a bar, you will use the diameter or the area of a circle. How about the welding heat input? The welding heat input is the amount of heat generated to the weld and is a function essentially of energy. As the heat input increases, the cooling rate of the material decreases. It is given by this formula, which is This V is the voltage, A is the amperes or the current in amperes, times 60 over the travel speed or the speed in which you deposit the weld onto the base metal. So the units here is joules, which is the measure of energy. Then, as I've mentioned earlier, V is the voltage, A is the welding amperage, and the travel speed is measured in inches per minute. How about this empirical formula of carbon equivalent right here? So this carbon equivalent is an empirical expression that determines the combined effects of varying alloying elements on the material's hardenability. This has an effect with what heat transfer or temperature levels that must be done to ensure weldability, especially of steel. So this carbon equivalent is normally used to measure the hardenability of steel. Generally, if you have a high CE or carbon equivalent, then the hardness or the tensile strength of that steel or that material increases. But if you have a low carbon equivalent, then that strength decreases. So not only carbon contributes to the hardenability of steel, but other elements as well, especially manganese and others, compute for the carbon equivalent to determine what will be the carbon equivalent, thus determining the strength or the hardness of that specific grade of steel. So I mentioned earlier that we will also tackle the conversion that is normally used in the CWI exam. So these are the common properties that you will need to remember during the exam. So the properties that you will normally encounter are the area dimensions, density, deposition rate, flow rate, heat input, linear measure, mass, pressure, temperature, tensile strength, travel speed, vacuum, and wire feed speed. So how will you use this chart? So for example, you will convert inch squared to millimeter squared. Then you just multiply whatever value here. For example, 1 inch squared, you will just multiply it by 6.452 times 10 squared. So that is 1 inch squared times 645.2. Then you will automatically convert that into millimeter squared. So I have an example that will demonstrate how you can use this chart, and also I can also provide you how to memorize this chart without even reading it. So for example, in pressure, so you do not need to memorize all of these, you just need to remember the atmospheric pressures for the specific units that you will need to convert it with. By the way, I just want to let you know that I have a free PDF outlining these formulas and conversions together with sample exercises you can use for your review for the exam. Look for the video description below. So for our first example, so determine the diameter in inches for an electrode that measures 1.2 mm. So you just need to convert this 1.2 mm into inches. So 1.2 mm, you just need to multiply this by a conversion factor using the chart that I've shown earlier. So if you don't remember that chart, so you just need to remember this. So 1 inch is equal to 25.4 millimeters. So 1.2 mm, you just divide that by 25.4 mm. So you can cancel this unit. Then have it the numerator as 1 inch. So basically just divide 1.2 to 25.4. The answer here is 0.0472 inch. So if you may ask if you are allowed to use the calculator in the exam, so you can bring your own scientific calculator, but programmable calculators are not used. So another example of conversion here, determine the feed speed in inches per minute for a wire fed at a speed of 120 millimeters per second. So you need to convert 120 millimeters per second into inches per minute. So you have here 120 millimeters per second to inches per minute. So 120 mm per second, you just need to cancel those units and convert it to inches. So 25.4 millimeters, 1 inch, and for the seconds, you need to cancel the seconds on the denominator, so you have the conversion here. So 1 minute is equal to 60 seconds. So you put the 60 seconds on the numerator for you to cancel the units, then 1 minute on the denominator. So that leaves you with this one. As you can see, the remaining units are inches and minute. Operating that equation will give you 283.5 inches per minute of feed speed. So this is your answer. How about the conversion of diameter in millimeter to inches? So this is a common question in the CWI exam because it involves the electrode diameter. So as you can see, you can also memorize the conversion here. So linear measure from inches to millimeter, you have here the conversion factor of 25.4, meaning you will multiply the 25.4 value to the inch value to have it as millimeters. So 1 inch is equal to 25.4 millimeter, just like we showed earlier. So how do you convert this one? So 5/32 inch. So you need to cancel the inch unit. So 25. So 1 inch times 25.4 mm. So the inch unit will cancel now. So 5/32 times 25.4. So this is 3.96875 millimeters, or that is close enough to 4 millimeters. So how about the conversion of cubic feet per hour to liters per minute, or vice versa, liters per minute to cubic feet per hour? This is a measure of volume flow rate. So 22 liters per minute, you need to convert it to cubic feet per hour. So using the chart here, so liters per minute, you need to convert to cubic feet per hour. So you need to multiply the value of liters per minute by 2.119. 22 liters per minute times 2.119 will give you the value of cubic feet per hour. So 22 times 2.119 will give you 46.62 cubic feet per hour. So what if you don't want to memorize those charts? You'll need to find a way to convert liters per minute to cubic feet per hour. So 22 liters per minute. So we all know that 1 liter or 1 cubic meter is equivalent to 1,000 liters. And 1 meter is equivalent to 3.28 feet. So you put here 3.28 feet. But you need to raise this entire expression to 3. So operating this expression will give you the answer. 22 divided by 1,000 times 3.28 cubed times 60. So that will give you the same answer as earlier. So 46.58 cubic feet per hour. So how about the conversion of pressure from megapascal to pounds per square inch? So looking at the table here, you need to multiply the MPa value by 1.45 times 10 squared. So that is equivalent to 1 MPa is equal to 145 psi. So that is the conversion. So 198 MPa, multiply that by 145, then you will give, or you will get the result of the PSI value, which is 28,710 PSI by using the chart earlier. But what if you don't want to remember this value, this 145? So you have to remember to convert the pressure in terms of the atmospheric pressure. So you know that 1 atm is equivalent to 14.7 psi, and it is also equivalent to 0.101325 megapascal. It is also equivalent to 101.325 kPa. So you just need to remember these three values, so you can convert anything now from PSI to MPa to kPa and vice versa. So how do you utilize that conversion factor? So 198 MPa times, you need to convert this to PSI, so you'll need to multiply it by 14.7 PSI, but you need to cancel this MPa unit, so you have the conversion of 0.101325 MPa. So you can cancel the megapascal. So 198 times 14.7 over 0.101325. That will give you almost the same result as the first one, which is 28,725 PSI. So that will give you a close enough answer in the examination if you don't want to memorize the charts that I have shown earlier. So how about the welding heat input? So this is an essential formula for the CWI exam, as many of the questions will showcase this question or showcase the use of this equation. So a single wire submerged arc welding is operating at 32 volts, 600 ampere, and is traveling at 8 inches per minute. What is the heat input? So you have the given here, 32 volts, 600 ampere, and 8 inch per minute. So using the formula of the heat input, so V, or the voltage times the current, times 60 over the travel speed in inches per minute. So that is 32 volts times 600 amperes times 60 over 8 inches per minute. So that will give you an answer of joules per inch. So 32 times 600 times 60 over 8. So that will give you an answer of 144,000 joules per inch. So what happens in this formula is that this voltage in ampere is equivalent to joules per second, or watts. So you just convert this second into minutes. So times 60 seconds per minute. That's why you have a multiplier of 60 here. That's the reason. You have a 60 conversion factor in the numerator. So now the prevailing units, as you can see here, is joules per minute, because the seconds here will cancel, and inches per minute on the denominator. So if these minutes, both minutes are on the denominator, then you can cancel both of them. That will give you an answer of joules per inch. Hence the heat input in joules per inch. So for the calculation of ultimate tensile strength, so we have an example here. Calculate the ultimate tensile strength in megapascal of a tensile specimen having a cross-sectional area of 0.3 square inch and broke at a tensile load of 24,600 pounds. So if you can remember the formula of ultimate tensile strength, which is the force maximum, or Pmax, divided by the original cross-section, which is in this example, the 0.3 square inch. So 24,600 pounds divided by 0.3 square inch. So that will give you a value of 82,000 pounds per square inch, or PSI. So how about we use that example to calculate the ultimate tensile strength of the pipe? So if you may remember, the formula of UTS, or the ultimate tensile strength of the pipe, is P max over its cross-sectional area, which is 0.7854 times OD squared minus ID squared. So this is just the maximum force over the diameter of the cross-section of the pipe, which is pi over 4 times its outside diameter squared minus the inside diameter squared, because as you can see, the pipe has a hollow cross-section, meaning the inside diameter is hollow, and you have a thickness here, or the outside diameter here with a certain thickness, so that you will utilize that thickness in this equation as well. So the given here is the maximum force P max is 5,000 pounds. The OD is 10.75 inches, and the pipe thickness is 0.375 inch. So how will we get the internal diameter first, because we don't have the internal diameter? So drawing the cross section of the pipe, so we have the OD here and the ID here. So the dimensions we have here is that we have the OD as 10.75 inch, and this is the thickness, which is exaggeratedly 0.375 inch. So we can get the internal diameter by subtracting the OD to the twice of the thickness of the pipe, because you can measure the thickness as well on the other side, 0.375 inch, and this is now the internal diameter. So you multiply that by twice the thickness, or subtract that by twice the thickness. So ID is now 10.75 inch minus 2 times 0.375 inch. So that will give you 10 inch as your internal diameter. So going back to that formula, so UTS is now 5,000 pounds over 0.7854 times 10.75 squared minus 10 squared. So the unit of this one of the denominator is inch squared, because you square both of the dimensions in the denominator. So this will give you a value of 409.1 pounds per square inch. So that will be the ultimate tensile strength value of the specimen. So how do you calculate now the percent elongation of a bar with original length of 150 mm and it is stretched to 152.5 mm? So if you can remember, the formula of percent elongation is that it is the final length minus the original length all over original length. Multiply this expression by 100%. You get the percent elongation. So 152.5 mm minus 150 mm, divide that answer of that expression to 150 mm times 100%. So this will give you 152.5 minus 150 is 2.5 mm divided by 150 mm, multiply that by 100%. So this will give you a percent elongation of 1.67%. So that is the answer. So how do you know if a material passed the percent elongation or not? So that depends on the standard the material is governing with. So if it, for example, it is being governed by ASTM standard, ISO standard, so it has an acceptable percent elongation for which the material is acceptable to be stretched 2 at some point. So if it is stretched at a percent elongation lowered at some value, so it will not be acceptable because the material is brittle. So it doesn't have enough ductility to basically survive the force that it will be subjected with. So for the percentage reduction in area, so we have the original area of 2.5 square inch reduced to a final area of 2.15 square inch. So percentage reduction in area is given by the final area minus the original area all over the original area times 100%. So the final area here is 2.15 square inch minus the original area 2.5 square inch all over 2.5 square inch times 100%. So never mind the negative value that you'll receive here because it is a reduction. So meaning a reduction will automatically give you a negative value. So 2.15 minus 2.5 over 2.5. So that is times 100%, that is 14% reduction in area. So to determine the equivalent carbon, so we have this formula right here. So the equivalent carbon is equal to the percentage carbon plus percentage manganese over 6 plus percentage nickel over 15 plus percentage copper over 13 plus percentage molybdenum over 14. So we'll just substitute the value that we've got here in percentage. So it automatically gives us in percentage value. So we just directly substitute this into the equation. So the equivalent carbon here is 0.18 plus 0.34 over 6 plus the nickel value. We don't have the nickel here, so that is 0, plus the copper content, which is 0.35 over 13 plus molybdenum. So we don't have a molybdenum percentage for the ASTM A1065, so we will have that as 0 as well. So remember that for the elements that is not present in the chemical composition of a certain material, so you don't need to put that in the equivalent carbon equation. So 0.18 plus 0.34 over 6 plus 0.35 over 13. So that will give you an equivalent carbon of 0.2635% or 0.26% equivalent carbon. So the threshold for preheat for the need for preheat is 0.45. So if you exceed 0.45 equivalent carbon, so that means you will need to have this material preheated at a certain temperature. So the levels of preheat, as I've mentioned earlier, will depend upon the equivalent carbon that you have present in the material. So this depends depending on the material, but this is just a recommended value or a preset limit for the equivalent carbon for the material that will now be needed to be preheated, because as I've said earlier, not only the hardenability of the material is affected by the equivalent carbon, but also the weldability, because as the material gets thicker or gets harder, thicker and harder, the cooling rate decreases, thus the weldability of the material also decrease, because as you cool the metal, a lot of discontinuities can happen. So you need to preheat that in order for the metal to be easily weldable, and you can also use more acceptable or more commercially available electrodes for that